All right, my friends, welcome back. Don't forget to pick up a quiz on your way in. So today we're picking up where we left off last time. We're talking about hydroboration, oxidation of alkenes. And you want to put in your mind, you want to contrast this with the acid-catalyzed alkene hydration, because it's going to give you different results in two ways. First, you will see that at the end of this reaction, we're going to add water across, well, you're going to see that the OH in this reaction ends up on the less substituted carbon, and the hydrogen ends up on the more substituted carbon. But you're going to see the reason for that still has to do with the stability of, in this case, a partial positive charge on a more substituted carbon. So the outcome's different. OH is going to end up on the less substituted carbon. Hydrogen's going to end up on the more substituted carbon. But the reason is going to be similar to something that we've seen before, which is buildup of partial positive charge on a more substituted carbon where it's more stable. The second thing that distinguishes hydroboration oxidation of alkenes from acid-catalyzed alkene hydration is that we see syn addition exclusively, syn addition of hydrogen and OH to the same side of the original double bond. Okay? So to illustrate this, we'll show a simple example. This is going to be an alkene where you have carbon A and carbon B, and A is more substituted than B. And the reagents for this reaction, there are two reagents. One is BH3, that's the first reaction. This is the hydroboration reaction. And then the second reaction is the oxidation reaction. This involves hydrogen peroxide as an oxidizing agent and then NaOH as a base. This is the oxidation step. And you will see when this reaction is over, we're going to get two products that differ only in stereochemistry. So we're going to get a product where hydrogen is on the more substituted carbon A. It just so happens that in this product, carbon A is not a stereocenter. And then we'll have the OH on less substituted carbon B. And it turns out that carbon B is a stereocenter. We will see that the hydrogen and the OH end up on the same side of the original alkene as each other. And we'll see that you get both stereoisomers. That is, the stereoisomer that comes from addition from above, and then the stereoisomer that comes from addition from below. Okay? Both of them are syn addition products, and you will see that these two are actually enantiomers of each other. You get the two enantiomers from the fact that the alkene has a top face and a bottom face, and it can attack from either side with similar efficiency. So that's predicting the products. Go ahead.
Well, I was just going to say, I didn't quite get why it's more stable to have the, where did the partial positive charge?
Yeah, I didn't show you the mechanism yet. None of the yep, we're going there. So the question is, why does OH end up on the less substituted carbon? Why does hydrogen end up on the more substituted carbon? And where is this issue of stability? So Again, we're going to contrast with alkene hydration under acid catalyzed conditions. When you've seen alkene hydration before, so this is all in parentheses, this is the contrast. This is not the mechanism of hydroboration oxidation. I'm just reminding you of something we saw previously. In acid catalyzed alkene hydration, the thing that gets attacked in the first step is a hydrogen. The pi bond attacks the hydrogen. We make the hydrogen a new sigma bond between that hydrogen and carbon B so that there can be a full positive charge on carbon A. Because that positive charge is more stable on carbon A. And then in a second step, water acts as a nucleophile and attacks that positive charge from above or below. I'm skipping the final deprotonation step, but you would get this product from acid catalyzed hydration. Now we're going to contrast that with the mechanism of hydroboration. So, here is our alkene with carbons A and B. And then instead, for hydroboration, our electrophile is BH3. So in the alkene, which is our nucleophile, the HOMO is the carbon-carbon pi bond. In the electrophile, the LUMO is what? Empty p orbital on boron. There is the key difference. The LUMO for acid catalyzed hydration of the electrophile was the oxygen hydrogen sigma star, and it was mostly on hydrogen. Hydrogen was attacked first. Hydroboration switches that. Hydrogen isn't attacked first here. Instead, boron is attacked first. What happens next is going to need a little bit of explanation. You would predict, though, that because we exclusively see syn products, that there cannot be a carbocationic intermediate. If there were, you might expect things to be added in the second step from either side and to see a mixture of syn and anti-products. So let me talk you through this mechanism, show you the transition state, and then I'll answer some questions about it, because this is kind of challenging to understand. What happens is a concerted mechanism where we are going to form simultaneously the carbon-boron sigma bond and the carbon-hydrogen sigma bond, and we're going to break the boron-hydrogen sigma bond. All of that is going to happen in the same step. However, you're going to see that the reaction is asynchronous. That's a complicated term that basically means a concerted reaction can be asynchronous when some of the bonds are more formed than others. Okay? So we're going to see that the carbon-boron bond in the transition state is more completely formed than the more completely formed than the carbon-hydrogen bond. All right, so what do we mean by that? I'm going to draw arrow mechanism that show you how to do this first step. It's actually pretty easy. You're going to form a new bond as pi electrons attack boron, and then the boron-hydrogen bond is simultaneously going to break and go to the more substituted carbon. Excuse me, going to sneeze. Both of those things happen at the same time, and you're going to get two possible products in enantiomers of each other, and you're going to see that the boron that was attacked is here, and then the hydrogen is on the adjacent more substituted carbon. And you would expect to get the enantiomer of that in which the addition process happened from below. Okay? Now, we need to sort of deal with the fact that they end up syn to each other is explained by the fact that the reaction is concerted. There's no time for rotation around the bond between A and B that would allow you to deliver boron and hydrogen to different faces of the alkene. But the issue of why the boron ends up on the less substituted carbon and why hydrogen ends up on the more substituted carbon is a little bit more complicated, and to see that we need to draw what the transition state looks like. Okay, so I said that in this reaction, three things are changing at once, and I guess I should have added a fourth. We're also breaking the carbon-carbon pi bond. So you're going to see that the carbon-carbon pi bond and the carbon-boron sigma bond and the carbon-carbon pi bond are more completely changed in the transition state. So let me try to illustrate this. Oops. All right, this is carbon A, this is carbon B. I said that in the transition state, the carbon-carbon pi bond is mostly broken, mostly gone. If the carbon-carbon pi bond is mostly broken, I'm going to use sort of a sparse dotted line to indicate that it's mostly gone, okay? And I also said that the carbon-boron bond is mostly formed. So to indicate that, I'm going to use really dense dots to indicate that that bond is almost formed. And I'm going to put the boron pretty close to the carbon, okay? Now, I want you to ponder what the consequences might be of having the carbon-boron bond mostly formed and the carbon-carbon pi bond mostly broken. If the carbon-carbon pi bond is mostly broken, and I'm forming the bond with carbon and boron with carbon B, then what has to be happening to carbon A? Got to be getting a partial positive charge, right? So carbon A experiences a partial positive charge. Now, let's talk about what's happening to the boron. And I'm just going to draw the hydrogen here without drawing dotted lines just yet, so you can think about this. When boron is just BH3, it's neutral. If boron were bonded to four things, what would the formal charge be on boron? Be negative, right? So if the carbon-boron bond is mostly formed, that would mean that there has to be a buildup of partial negative charge on the BH3 reagent. Now, if we were doing formal charge, we would put that on the boron. But remember, formal charge doesn't really tell us too much about how electron density is distributed in a molecule. To do that, we have to use electronegativity intuition. And if you look up electronegativity values, it turns out that hydrogen is more electronegative than boron. So it turns out that that partial negative charge is actually felt out here on the hydrogen. So the consequence of the carbon-carbon pi bond being mostly broken is that there is a buildup of partial positive charge on A where it's more stable. And the consequence of the carbon-boron bond being mostly formed is that there is a buildup of negative charge on the hydrogen. Okay? And so, as the reaction progresses, and again, I'm going to show the boron-hydrogen bond is still mostly formed. And then I'm going to use a sparse dotted line here to indicate that the carbon-hydrogen bond with carbon A is not very formed. You can begin to see where the regioselectivity comes from. We formed the first bond with boron with less substituted carbon B so that the buildup of positive charge can happen on more substituted A where it's more stable. Then hydrogen gets delivered to A because the hydrogen has a buildup of negative charge on it, and A is where the positive charge is. Yeah?
You're saying that B is less substituted than A?
Carbon B is less substituted than A.
Is that because, like, A and B are both connected to two separate things, but on B it's a hydrogen?
Yeah. Yeah, and yeah, substitution refers to non-hydrogen things. We pay attention to that because non-hydrogen things have adjacent CH bonds that can do hyperconjugation. Yep. Okay. So this transition state, we'll add the bracket and the double daggers to make the point, explains why the boron ends up on the less substituted carbon and the hydrogen ends up on the more substituted carbon. And now you can sort of see what's going on with these two arrows. The two arrows communicate these four things. The carbon-boron bond forms as the carbon-hydrogen bond is the carbon-carbon pi bond is breaking. And then H takes its electrons, leaves from boron, and attacks the more substituted carbon where the buildup of positive charge is. Okay, questions about that hydroboration step? If you understand the mechanism in detail, then you know why it's a syn addition, because it's concerted, and then you know why the why the BH2 ends up on the less substituted carbon, and that's because it's asynchronous. The carbon-carbon pi bond is mostly broken, and the carbon-boron bond is mostly formed. Yes?
So the syn and anti we get, like the two, the racemose mix that we get is from the fact that the pi bond can attack from the bottom.
Right, the pi bond's got two faces, and it can attack the boron from the top face or the bottom face.
But then we're not getting the other two from like, that we got from a planar carbon cation.
That's right, you're not getting the other two variations that you would get if you went through a planar carbocation. Yes, go ahead.
And asynchronous just means that one bond is more formed than another?
That's right. Yeah, asynchronous. Concerted means it's all happening in the same step. Asynchronous means some bonds are more formed or broken than others are. Okay, good. So let's now, right. So that's just hydroboration. Now we need to do oxidation. These are your hydroboration products. Now, fortunately, the oxidation step, we're not going to learn the mechanism of it. The mechanism is known, but it's one of those things where the juice may not be worth the squeeze. If you want to see the mechanism, it's in the study guide. You can look at it, but spending a lot of time on it doesn't actually help us that much in this class. I used to do it, and then I stopped doing it because I felt like it wasn't that useful. you want to see it, it's in the study guide, but all you need to know for the oxidation step is that we are going to replace BH2 with OH, and there is going to be no change in stereochemistry, which tells you that this is not a traditional SN2-like substitution reaction. But if you want to see what the mechanism is, again, it is in your study guide, and you can look at that in more detail. But we're going to gloss over it and ignore it. And yes, I promise not to ask you questions about the oxidation mechanism of the hydroboration oxidation reaction series. These are the two products that you get, and importantly, the OH and the hydrogen end up on the same side of the original alkene, with the OH on the less substituted carbon and the hydrogen on the more substituted carbon. But again, you still only see syn products. Okay? So that's, you know, the mechanism of the first step, the mechanism of that second oxidation step, you're not going to know unless you really want to look at it in the study guide, but I'm not going to ask you questions about it. Yes?
Now that you explained what the mechanism you need to know, you said earlier that it's not like something else. Could you explain
I said this is not the replacement of OH for BH2 is not an SN2 reaction because there's no change in stereochemistry. Yeah. So I'm just saying, the reason I'm saying that is because when I don't show you the mechanism, some of you might be inclined to imagine in your mind what it's like, and if you imagine it as SN2 and you do the stereochemistry switch with SN2, you're going to get the wrong answer. Okay, so let's practice. You have before you a quiz. Question 1 has 3 things in it. I only want you to do the first one. The second 2 have starting materials that are alkynes. That's a little bit different, and we are going to talk about that next. But first, I want you to do this. So you are welcome to draw the hydroboration product as an intermediate, and then draw the final oxidation product, or you can just skip ahead to the final oxidation product. There, you should get 2 products from this first reaction. Do. How you doing? Need some more time? Yes? Okay. Oh, just as a reminder, deuterium, I think you've seen this before from last time. D, or deuterium, is just an isotope of hydrogen. It functions exactly like hydrogen. It's just you can tell the difference between it and hydrogen experimentally. All right, carry on. Okay, let's take a look. So, of the two carbons, A and B, which one gets the OH? B, right, because it is the less substituted carbon. And we learned about that mechanism. So I'm going to draw the OH as either a dash or a wedge to indicate that the first hydroboration step can happen from either the top face or the bottom face of the alkene. Now, if OH is on B, then hydrogen should be on A. Should I draw my hydrogen on A as a dash or a wedge for this structure on the left? Wedge. It's got to be syn. Good. And then here is the methyl group. Similarly, here is the hydrogen, here is the methyl group. You exclusively see syn addition products, but you do get a pair of enantiomers. Okay? All right. Yes?
So if one of them wasn't a stereocenter, then would it not matter? So like in the top one, you didn't have an extra methyl bond?
Right. So the question is, suppose on the top carbon, suppose carbon A, what's the best way to do this? I'm trying to think the only way I could come up with an example where that would, I know what you're asking. You're asking is, are there times where you can't tell that it was syn addition? And I'm going to go back to the example we did above. If you notice in the final product, the OH is at a stereocenter, but the hydrogen is not. So you actually can't tell that it was a syn addition there. Yeah, it was, but if it's not a stereocenter, you can't tell. Yep. And that's why I deliberately chose this example where both of the products would be stereocenters, so you can tell the difference. Yes?
Why do we need the hydrogen peroxide in the second step? Is that just
Yeah, why do you need the hydrogen peroxide in the second step? That has to do with the mechanism. So it's not the oxygen that replaces the boron actually comes from the hydrogen peroxide and not OH minus. For details, stay tuned and watch them, look at the mechanism in Study Guide 10 if you want to. Yeah? If there's not a stereocenter, is it still valuable to show the geometry? Sure, but not required. If it's not a stereocenter, you don't need to show the dashes or wedges. Yep. Okay, good. Others? So I decided kind of on a whim last night to change a little bit about how I teach chapter 10. You'll notice that there are two examples of alkynes here as starting materials. That's new. We haven't done anything with alkynes very much so far. Now, to understand why we're doing this, you need to know a little bit of history, and it doesn't matter to you, but when you get old like me, there's a little bit of experience involved. Long before you guys had the current version of the textbook, edition 6, many, many years ago, we used edition 5. I know that will surprise you. And in edition 5, there was a chapter 10 on alkenes, like we've done, and then a chapter 11 on alkynes that basically took the alkyne and subjected it to all 5 of the reactions that we did in chapter 10 for alkenes, and gave you products that mostly made sense, but in some respects it was duplication, and it seemed like a waste of time. So the text publisher, in response to criticism that said, hey, you should add more biology to your OChem textbook because most of your students are in the life sciences and they need to know the chemistry of biology. So in response, the publisher said, okay, we'll add some chapters on biological macromolecules, but we want to still keep the total number of chapters the same, so we need to remove some stuff. Well, instead of removing stuff, they took all of the stuff about alkynes in chapter 11 and they crammed it into chapter 10 and called it still just chapter 10, which I thought was silly, and so I didn't really teach the stuff on alkynes much anymore. But it turns out there are two reactions of alkynes that are useful to know, and mostly because they prepare you for some things in 352. So these are not in the study guide, they are in the chapter. We'll talk about them here in class. Then you can go and read in the chapter about these two reactions if you need a little bit of help on them. It turns out that we're going to do them mostly by analogy to what we've done with alkenes so far, and I'll take you through it. Yes, please. How often are alkynes found organically? They're not found a lot in nature. There are some strange natural products that have alkynes in them, but they're not found a lot in biology. Yes?
Since it's not on the study guide, will this be on the test?
Since it's not on the study guide, will it be on the test? Well, that's a good question. I intend to put it on the problem set, and I do want you to know what we'll talk about today. So you'll have some practice from it on the problem set. The only difference is you're going to have to go to the text and do some practice problems if you want to, if you need help beyond what we've talked about today. I think what we'll do today is going to prepare you well enough so you shouldn't need a ton more additional work. Okay. So that was a yes. All right. So alkyne hydration under acidic conditions, we're going to do exactly by analogy to alkene hydration under acidic conditions. And that is, recall that if you have an alkene that looks like this, and you subject it to H2SO4 and water, your product has the OH at the more substituted carbon because you go through a carbocationic intermediate where you add the hydrogen to the less substituted carbon first so that the positive charge can be on the more substituted carbon in the intermediate, okay? There's a carbocationic intermediate. And I'm abbreviating things in strange ways, and that's all right. Sorry. So we are not going to do the mechanism of, we're not going to worry about the mechanism to get from this alkyne starting material to the alcohol product. We will learn a mechanistic step after that, but we're not going to learn this mechanism. We're just going to think of it as analogous to the mechanism with alkenes. So this particular alkyne is called a terminal alkyne. That's because you have one of the two carbons of the alkyne that's bonded to another carbon and one that's bonded to a hydrogen. Another name for a terminal alkyne is an acetylene. So if you look at the alkyne and compare it to the alkene alkenes was a nucleophile and the HOMO was the carbon-carbon pi bond. For the alkyne, the HOMO is also a carbon-carbon pi bond, only we have two. Now, they're independent of each other. They're equal in energy. It doesn't matter which one does the reacting, but we will see that only one of them does the reacting. The other one doesn't participate. So we're not going to show that mechanism, but it would happen exactly analogous to what we saw above for alkenes. That is, pi electrons attack the hydrogen oxygen sigma star, we break that bond, we add the hydrogen to the less substituted carbon so that the more substituted carbon could have a positive charge, and then water comes in and attacks the more substituted carbon to give us our alcohol. We're not going to do that mechanism with alkynes, and I won't ask you questions about the mechanism for alkynes, but you should be able to understand why this is the product. The OH ends up on the more substituted carbon, and the hydrogen ends up on the less substituted carbon. Now, actually, there was some concern and questions during the first hour. Does the hydrogen and the OH get added to the same side of the alkyne? Should they be cis to each other in this product? The answer is no. You'd expect both cis and trans, though in this case you can't tell, right? Because both things on this carbon are hydrogen, so you can't tell what cis or trans. Just to highlight the point that the hydrogen gets added to the less substituted carbon, I'm going to highlight one of them, but don't be worried about the stereochemical issues. It doesn't end up mattering for reasons I will show you now. This intermediate is called an enol because you've got an alkene and an alcohol in the same molecule, and the OH is attached to one of the carbons that's involved in the alkene. This is an enol, and it turns out that enols are in equilibration with a more stable alternative isomer, a more stable regioisomer, a constitutional isomer. And here is what that constitutional isomer looks like. This is a ketone. The pi bond is now between carbon A and the oxygen, and a hydrogen that used to be on the oxygen is now over here on carbon B. These two, the ketone, or we'll call this the keto form of the molecule, and the enol form of the molecule, they are isomers of each other, and they are constitutional isomers because they differ in connectivity. We'll see that they're a specific kind of constitutional isomer, and that is, we're going to call them tautomers because they differ only in the location of a hydrogen and a pi bond. And that word will be important to you in 352. When you get to 352, your instructor is going to expect you to have heard of tautomerization before and to have worked through it. And we're going to do that mechanism. But the final product of acid catalyzed hydration of alkynes is this ketone, where the oxygen is on the more substituted carbon. Now, stay tuned for the mechanism here, but I want to show you, we will do the mechanism, so stand by. But before we do that, I want to contrast the results of acid-catalyzed alkyne hydration with hydroboration oxidation of alkynes. And again, we're going to do this not by drawing the mechanism of the hydroboration and oxidation steps, but we're simply going to do this by analogy to what we did with alkenes. That is, we know in the hydroboration oxidation reaction, the OH ends up on the less substituted carbon, and the hydrogen ends up on the more substituted carbon. Only one of the two pi bonds reacts, so we get this product. And it turns out here you do see syn addition of the hydrogen and the OH. though as before, it will turn out not to matter because the pi bond is gone in the final product and there are no stereocenters in the final product. So this is also an enol. It differs from the enol above in that the OH is on less substituted carbon B instead of more substituted carbon A. And then this tautomerization process will happen, and tautomerization will change the location of the pi bond and the hydrogen attached to the oxygen. The hydrogen will actually end up on carbon A, and the pi bond will actually end up with the oxygen on carbon B. And notice that this keto form of the enol is different from the keto form above. This one is an aldehyde and not a ketone because the oxygen is on the less substituted carbon. Do you see sort of the analogy to the alkene chemistry, all about where the oxygen ends up? So far, you should be okay, I hope, getting from the alkyne to the enol, but you may be uncertain about how the enol ends up as either the aldehyde or the ketone. That's fine, because I haven't showed you that mechanism yet, and I'm going to. Before I do, I want you to take the next 60 seconds based on what we've just talked about. Okay, 90 seconds, maybe. And show me the products. And I want to see the final keto form, though if you want to draw the intermediate enol, you can. Show me the products for the hydroboration and then acid catalyzed hydration of this alkyne. It should be very similar to the notes, only here I'm showing you what the R group is on the alkyne. Just as a little hint, by the way, sometimes if you're unfamiliar with alkynes, because the line isn't bending, there is a carbon here and a carbon there. Okay, for hydroboration, oxidation of the alkyne, where does the carbon-oxygen double bond end up? On A or B? That's backwards. For acid-catalyzed hydration, the carbon-oxygen double bond ends up on A, more substituted A, and you get a ketone. Whereas for hydroboration oxidation, the carbon-oxygen double bond ends up on less substituted carbon B. Yes?
Can you draw the enol, please?
Yes. Yep, let's draw the enol real quick. The enol for hydroboration oxidation would look like this. The enol for acid catalyzed hydration would look like this. Okay? Now I understand that's a big jump to go. It's not such a big jump to go from alkyne to enol, if you're following what you've learned with alkenes so far. It is a bigger jump to go from enol to keto form. That looks like magic chemistry. Yeah.
So because the boron is involved in getting the alcohol onto a molecule, is that why it's on the less substituted than the low? I think I'm lost in why it's on the more substituted.
Right. So the reason hydroboration oxidation ends up with the OH on the less substituted carbon has to do with the mechanism of that reaction that we talked about earlier, where the carbon-boron bond forms first with the less substituted carbon so that the buildup of partial positive charge can be on the more substituted carbon. Whereas alkyne and alkene hydration involves a carbocationic intermediate where you want the positive charge to be on the more substituted carbon. What I want to do, go ahead.
For the aldehyde, does it need to, does the chain, the carbon chain need to look like that? Or could you the, like the.
So for the aldehyde, you are welcome to draw it any way you want as long as the connectivity is correct. Yep. Would I consider the enol and the keto form a product? No, the final product is the keto form. And I want to show you now how to convert between the keto and the enol. So this process, the tautomerization process, can happen under both acidic conditions and under basic conditions. So let's do basic conditions first, because these are the conditions that apply for hydroboration oxidation. So here is your enol for hydroboration oxidation. Under basic conditions, OH minus can deprotonate the alcohol of your enol, and that leads to an intermediate, and I'm using equilibrium arrows to, but that'll confuse you, so we'll just not. That will get you to the following intermediate, which is the conjugate base of the enol. And the conjugate base of the enol is actually called an enolate, and we will deal with enolates a lot in 352. Enolates have a resonance structure in which the negative charge from the oxygen is actually on the adjacent carbon, which we're calling A. Right? And so, if the enolate picks up a proton on the negatively charged oxygen, it just goes back to the enol. If it picks up a proton on the negatively charged carbon, it becomes the keto form. You can draw the mechanism for forming the keto form either from the resonance structure on the left or from the resonance structure on the right. I got my left and my right mixed up, sorry. You can draw the mechanism either way, and either way is fully equivalent. Okay? It's just two proton transfer steps via a resonance stabilized intermediate. Now, under acidic conditions, you can do something similar. These are the conditions that would apply for acid catalyzed alkyne hydration. Under acid catalyzed conditions, you're going to do just what you've done before for alkenes, which is pi electrons attack the hydrogen. The new carbon-hydrogen bond will be with less substituted carbon B so that the positive charge can be on more substituted carbon A. And it gets better than that because if the positive charge is on A, lone pair electrons on the oxygen can kick down and form a resonance structure in which that positive charge is now on the oxygen. And now, hopefully, you're beginning to see where we get the final product. We regenerate our acid as water removes a proton from the positively charged oxygen, and that will get us to the ketone product. Okay, so we'll talk about that a little bit more next time. Don't forget to turn in your quiz on the way out. There is a synthesis problem on the end of your quiz. We didn't have time for it today. We'll talk about it next time, but it would help if you could work on it in the meantime between now and then, and I'll post the quiz on the content page of Learning Suite so you can do that.